Week 10 focused on answering the question, are alternative transportation options sustainable? In your course material and discussions, you explored the answers to these questions related to sustainable transportation. What are alternative transportation options? How do alternative transportation options work? What sustainability implications are associated with alternative transportation options? What factors affect how these implications change over time and space? And how can we compare these implications quantitatively through sustainability indicators? As you may have noticed if you looked over some of the optional course materials this week, there are way too many alternative transportation options to cover in one week. I chose to focus on the options that are currently poised to be the most likely near-term options, including two types of biofuels, biodiesel and ethanol, along with electricity, hydrogen, natural gas, unconventional oil, and efficiency and conservation. The United States Department of Energy's Alternative Fuels Data Center provided much information on how these alternative transportation options work and the sustainability impacts associated with them. Flex fuel vehicles are vehicles that can operate on a gasoline-ethanol blend in which there is a higher percentage of ethanol than gasoline. FFVs have one fueling system, which is made up of ethanol-compatible components, and a powertrain controller calibrated to accommodate the higher oxygen content of E85. Almost any plant-based material can be an ethanol feedstock, the material used to make ethanol. All plants contain sugars, and these sugars can be fermented to make ethanol in a process called biochemical conversion. Plant material also can be converted to ethanol using heat and chemicals in a process called thermochemical conversion. This table shows the potential yield of some commonly considered feedstocks in gallons per dry ton of feedstock used in the conversion process. Nearly all ethanol is currently derived from starch and sugar-based feedstocks. The sugars in these feedstocks are easy to extract and ferment, making large-scale ethanol production affordable. Corn is the leading U.S. crop and serves as the feedstock for most domestic ethanol production. Small amounts of wheat, milo, and sugarcane are used, although the economics of these are not as favorable as corn. The Renewable Fuel Standard limits production of ethanol from starch-based feedstocks to 15 billion gallons to ensure that there are enough feedstocks to meet demand in livestock feed, human food, and export markets. Cellulosic feedstocks are non-food-based feedstocks that include crop residues, wood residues, dedicated energy crops, and industrial and other wastes. These feedstocks are composed of cellulose, hemicellulose, and lignin. Cellulosic feedstocks offer many advantages over starch and sugar-based feedstocks. They are more abundant and can be used to produce more substantial amounts of ethanol to meet U.S. fuel demand. They are waste products, or in the case of trees and grasses, grown specifically for ethanol production, can be grown on marginal lands not suitable for other crops. Less fossil fuel energy is required to grow, collect, and convert them to ethanol, and they are not used for human food. There are challenges with harvesting, collecting, and delivering cellulosic feedstocks. Researchers are studying these challenges in an effort to formulate solutions to them. Vehicles that run on biodiesel are basically just conventional diesel vehicles as long as the blend of diesel and biodiesel includes less than 20% biodiesel. Biodiesel can be manufactured from vegetable oils, animal fats, or recycled restaurant grease. Like petroleum diesel, biodiesel is used to fuel compression engines and compression ignition engines, which normally run on petroleum diesel. B20, which is 20% biodiesel, and lower level blends generally do not require engine modifications. Engines operating on B20 have similar fuel consumption, horsepower, and torque to engines running on petroleum diesel. A natural gas vehicle uses either compressed or liquefied natural gas. CNG, compressed natural gas, is more widely available than LNG, or liquefied natural gas, and more appropriate for light-duty vehicles like the one shown here. CNG enters the vehicle through the natural gas fill valve, A, and flows into high-pressure cylinders, B. When the engine requires natural gas, the gas leaves the cylinders and passes through the master manual shutoff valve, C. The gas travels through the high-pressure fuel line, D, and enters the engine compartment. Gas enters the regulator, E, which reduces the gas pressure used for storage, up to 3,600 psi, to the required vehicle fuel injection system pressure. The natural gas solenoid valve, F, allows natural gas to pass from the regulator into the gas mixer or fuel injectors. The solenoid valve shuts off the natural gas when the engine is not running. Natural gas mixed with air flows down through the carburetor or fuel injection system, G, and enters the engine combustion chambers where it is burned to produce power, just like gasoline. There are three main types of electric vehicles: hybrid electric vehicles, or HEVs, plug-in hybrid electric vehicles, or PHEVs, and all-electric vehicles, EVs. HEVs typically have an internal combustion engine and electric motor, and can be powered by an alternative fuel or a conventional fuel, along with a battery, which is charged through regenerative braking. The vehicle is not plugged in to charge the battery. PHEVs are plugged in because they have a bigger battery than HEVs, and usually a smaller fuel capacity. EVs do not have any fuel tank and operate completely on battery power, which must be recharged by plugging it in. Like electric vehicles, fuel cell electric vehicles use electricity to power a motor located near the vehicle's wheels. In contrast to other electric vehicles, fuel cell vehicles produce their primary electricity using a fuel cell powered by hydrogen, rather than a battery. During the vehicle design process, the vehicle manufacturer controls the power of the vehicle by changing the fuel cell size, and controls the amount of energy stored on board by changing the fuel tank size. This is different than a battery electric vehicle, where the amount of power and energy available are both closely tied to the battery size. The most common type of fuel cell for vehicle applications is the polymer electrolyte membrane, or PEM fuel cell. In a PEM fuel cell, an electrolyte membrane is sandwiched between a positive electrode, the cathode, and a negative electrode, the anode. Hydrogen is introduced to the anode and oxygen, usually from air, to the cathode. The hydrogen molecules break apart into protons and electrons because of an electrochemical reaction in the fuel cell catalyst. Protons travel through the membrane to the cathode. The electrons are forced to travel through an external circuit to perform work, providing power to the car, then recombine with the protons on the cathode side, where the protons, electrons, and oxygen molecules combine to form water. Hydrogen is a secondary energy source, like electricity, so it has to be produced from a primary energy source. There are a lot of different ways to produce hydrogen, and many of them are summarized here. The primary challenge for hydrogen production is reducing the cost of production technologies to make the resulting hydrogen cost competitive with conventional transportation fuels. Government and industry research and development projects are reducing the cost as well as the environmental impacts of hydrogen production technologies. Creating an infrastructure for hydrogen distribution and delivery to thousands of individual fueling stations presents many challenges. Because hydrogen contains less energy per unit volume than all other fuels, transporting, storing, and delivering it to the point of end use is more expensive. Building a new hydrogen pipeline network involves high initial capital costs, and hydrogen properties present unique challenges to pipeline materials and compressor design. There are trade-offs between centralized and distributed production to consider. Producing hydrogen centrally in a large plant cuts production costs, but boosts distribution costs. Producing hydrogen at the point of end use, at fueling stations for example, cuts distribution costs but boosts production costs because of the cost to construct on-site production capabilities. Because hydrogen has a low volumetric energy density, it is important for a fuel cell vehicle to store enough fuel on board to have a driving range comparable to conventional vehicles. Some hydrogen storage technologies are available and undergoing more research and demonstration, and the volume needed for some of these technologies to achieve greater than a 300-mile range is presented in this graph. These alternative fuel vehicles are on the rise in the United States, as you can see from this graph. Federal and state policies have helped accelerate this trend and have largely focused on increasing ethanol use, which is why you can see the purple segment representing ethanol has increased the most rapidly over the last 15 years. There are many other ways to improve efficiency and conserve fuel, including improving the fuel economy of conventional vehicles through more stringent CAFE standards, using mass transit, active transit, ride sharing, car sharing, idle reduction techniques, new parts and equipment, maintaining vehicles properly, improving driving behavior, and resizing commercial fleets. In addition, low rolling resistance tires, super single tires, aerodynamic equipment and vehicle design, fuel tracking devices and telematics systems, speed control modules, synthetic oil, proper tire inflation, energy conserving motor oil, and engine tune-ups can all help reduce fuel use and improve efficiency. Corporate average fuel economy, or CAFE, standards are set periodically by the federal government to ensure vehicles are keeping up with the times. CAFE standards have been so effective since implemented in 1975 that fuel consumption did not increase in the United States from 1978 to 1990, saving nearly 2.8 million barrels of oil per day, about 25% of all gasoline demand. New fuel economy standards through 2025 are expected to save Americans $1.7 trillion and 6 billion metric tons of CO2 over the duration of the program. Also reduce oil consumption by an estimated 2.8 million barrels per day, which is more than we import from any country. This is expected to grow to 4 million barrels per day as older, less efficient vehicles are replaced with newer ones. However, improved efficiency of conventional vehicles pales in comparison to the efficiency improvements that are possible with a switch to hybrid and electric vehicles. Ride sharing is an energy conservation measure. Ride matching systems help commuters coordinate their rides by identifying potential matches based on location and schedule. Ride matching websites can feature rider or driver reviews, payment transfers, fuel savings calculators, and options for finding backup rides for special circumstances. The National Center for Transit Research maintains a list of ride matching systems, which you can access here and through the DOE Alternatives Fuel Center. Car sharing is another energy conservation measure. Car sharing programs provide individuals and companies with vehicles for limited use. This service is popular in metropolitan areas where not everyone owns a car, and for companies that need specialty vehicles only occasionally. Members gain some of the benefits of vehicle ownership without all the costs. Car sharing programs such as City Car Share charge an annual membership fee and an hourly fee for use. Other programs like Philly Car Share let members choose from rate plans based on their needs. Car share services such as Zipcar have found their participants drive fewer miles every year than car owners. Some car sharing companies even offer alternative fuel vehicles, such as all-electric vehicles. Active transit is human-powered transportation, such as biking and walking. Active transportation eliminates vehicle miles traveled altogether. So this alternative transportation mode is an effective way to conserve fuel and reduce vehicle emissions. Bike share programs provide bicycles for short-term use, typically near busy locations, conducive to one-way bicycle trips. Some travelers prefer shared bikes to bicycle only one segment of a trip, or to avoid the cost of purchasing, maintaining, and storing a bike. Memberships and payment schedules usually encourage many short trips over fewer long trips to minimize bicycle downtime. As one example, Capital Bike Share partners with public and private organizations to make more than 1,500 bicycles available at more than 160 stations across the Washington, D.C. metro area. Using multiple modes of transportation is the best approach for some individuals and companies to conserve fuel and reduce vehicle miles traveled. Between ride-sharing, mass transit, and active transit, travelers have many alternative transportation options. There are some online tools available to help people figure out what transit option is best for their individual needs. Open Trip Planner Map is an example of this type of online tool. It helps Portland, Oregon travelers plan trips through a combination of transportation modes including transit, bus or train, walking, and bicycling. An evaluation by the Oregon Transportation Research and Education Consortium found that targeted, customized information marketed to individuals was effective at changing traveler behavior. All of these alternatives have sustainability implications, and you covered a lot of information about these sustainability implications this week. Hopefully you kept a chart like this handy to keep track of all the information. I have included my spreadsheet below the link for this video, so you can review the information I compiled from this week's course materials for each alternative transportation option. This chart also compares many of these choices across several sustainability indicators. In terms of per-passenger fuel economy, intercity rail is among the top of the list due to high ridership and energy efficiency. Motorcycles are also very high because of their high fuel efficiency. Passenger cars and light trucks are toward the bottom of the list, and transit buses are actually one of the lowest because of low ridership rates currently. The video Sustainable Thurston provides some insight as to why this is the case by discussing the land-use transportation connection. In particular, the places we live are the biggest indicator of how we will choose to get around. Most Americans are willing to walk up to a quarter mile to get the things they need. So the more places you have within a quarter mile, the more likely you're going to walk. You're also more likely to take a bus if it comes every 15 minutes and goes right to where you're headed. But a 15-minute bus service only makes sense economically where you have the right combination of housing, services, and jobs at sufficient densities. Neighborhoods that average 10 housing units per acre mixed with commercial areas with 12 employees per acre are typically the minimum amount needed for transit buses to be economical and efficient. But even in dense urban areas, people will continue to rely on cars for most of their travel needs. How far they have to drive and how efficiently they can travel is directly related to land use and how communities grow. Connected streets and designing streets and neighborhoods with how travel will happen in mind will help make transit more efficient with lower out-of-pocket costs for everyone. In most cases, compact transit-oriented development, including multi-family housing rather than single-family housing, automatically uses the least energy per person. Because of these issues and trends, land use and development policies we set now have a big and lasting impact on future energy use in transportation. In terms of economic sustainability, electric vehicles are actually one of the most consistently cost-effective options. The Clean Cities Alternative Fuel Price Report provides regional alternative and conventional fuel prices for biodiesel, compressed natural gas, ethanol, hydrogen, propane, gasoline, and diesel. This chart from the Clean Cities Alternative Fuel Report shows average monthly retail fuel prices in the United States from 2000 to 2014. The price of petroleum fuels, gasoline and diesel fuel, is the primary driver of overall fuel prices. For as petroleum prices rise, so does demand for alternative fuels. As gasoline prices increase, alternative fuels appeal more to the vehicle fleet managers and consumers. Like gasoline, alternative fuel prices can fluctuate based on location, time of year, and political climate. Most biofuels are consistently higher than gasoline and diesel prices. State and federal incentives help reduce the cost of alternative fuels. There are alternative fuel tax rates in the state of Maine, shown here by fuel type in this table. In addition, there are many other state, federal, private, and/or utility incentives, including the Maine Biofuels Production Tax Credit, biodiesel fuel tax exemption, state plan to reduce petroleum consumption, provision for establishment of clean fuel vehicle insurance incentives, low-speed vehicle inspection exemption, commercial plug-in electric vehicle grant program by Central Maine Power, plug-in electric vehicle infrastructure development policy, idle reduction weight exemption, idle reduction requirement, along with the federal tax credit of $2,500 to $7,500 for plug-in hybrids and all-electric vehicles. This website allows you to compare the cost and environmental implications of specific vehicles based on your particular usage patterns. Life cycle greenhouse gas emissions include emissions from well to wheel, including extracting, producing, and using various fuels. This chart compares life cycle greenhouse gas emissions for many alternative fuels. Corn ethanol is nearly identical to reformulated gasoline, while ethanol from sugarcane and forest waste perform much better. Electricity based on the California grid mix has significantly reduced greenhouse gas emissions compared with gasoline, and so does hydrogen from natural gas. This graph shows a different picture because it includes the vehicles that actually use the fuels, and it compares life cycle greenhouse gas emissions for different means of commuting in terms of grams per passenger kilometer, meaning the emissions from transporting one passenger 1 kilometer in distance. All figures here are from Transport Canada's Urban Transportation Emissions Calculator and assume 100% city driving based on Canadian average emissions for each vehicle category. This graph shows the diesel transit bus with 40 passengers and the electric trolley bus to have the lowest emissions per passenger kilometer, other than biking and walking. And conventional gasoline and diesel, light trucks and SUVs have the highest emissions. Results based on U.S. data would be pretty similar. Greenhouse gas emissions depend greatly on the type of energy that is used to process the fuels. Corn-based ethanol can reduce life cycle greenhouse gas emissions by 19 to 52% compared to gasoline, depending on whether the U.S. average electricity mix, natural gas, or biomass is used to power the ethanol production process. Using cellulosic ethanol provides an even greater benefit, reducing greenhouse gas emissions by up to 86%, mainly because the cellulosic ethanol production process can use more waste biomass materials for any energy production during the ethanol processing stage. Recent studies have shown the importance of incorporating assumptions about future crop production rates and land use into life cycle analyses. These factors can substantially affect net greenhouse gas emissions calculations. Depending on the primary energy source used to generate electricity, electric vehicles result in substantial improvements in greenhouse gas emissions and total fuel cost. This table compares greenhouse gas emissions and fuel cost for a 100-mile trip for conventional and electric vehicles based on the U.S. electricity mix. The Department of Energy Alternative Fuels website allows you to compare the environmental impact of electric vehicles by location. You can type in your zip code and see how results vary compared to the national average. Here you can see that electric vehicles using Maine's electricity mix perform much better than the national average. This doesn't exactly show the true picture for Maine, however, because the electricity mix the DOE uses in this calculation is actually the mix for all of New England, not just Maine. Maine has a much higher share of renewables than the rest of New England, and therefore electric vehicles in Maine would perform even better than what is shown here. The fact that the results of the model for Maine are actually reflective of New England rather than Maine underscores the need to be aware of assumptions used in calculations like this. Therefore, I required that you read this page, which outlines all of the assumptions used in the greenhouse gas emissions calculator. There are also substantial variations in greenhouse gas emissions from hydrogen fuel cell vehicles. Argonne National Laboratories report fuel choices for fuel cell vehicles, well-to-wheels energy and emissions impacts, analyzed greenhouse gas emissions for 10 of the most common hydrogen production and distribution pathways. Argonne found that gaseous hydrogen produces fewer greenhouse gases than liquid hydrogen in most cases. Argonne also investigated hydrogen's effects on petroleum use and found that using hydrogen as a fuel reduced petroleum use by nearly 100% regardless of fuel pathway. Relative to gasoline vehicles fueled by reformulated gasoline, hydrogen production for all fuel pathways creates fewer greenhouse gas emissions, except when the fuel is produced by electrolysis from typical U.S. grid electricity. The PEW Center report you read, called Reducing Greenhouse Gas Emissions from U.S. Transportation, compares possible future CO2 emissions reductions based on different combinations of the alternatives we are studying this week. These potential reductions below 2010 levels achieved in 2050 range from 17% in the low mitigation case to 65% in the high mitigation case. Technological improvements to vehicle energy efficiency, low carbon energy sources, and all other strategies make roughly comparable contributions to greenhouse gas mitigation in the high mitigation case. In other words, no single technology, policy, or mode is able to accomplish a 65% reduction in total transportation greenhouse gas emissions. Achieving reductions of that magnitude requires a comprehensive strategy with strong public support, sustained by rapid technological progress. In other words, there is no silver bullet to reducing greenhouse gas emissions in the transportation center. It is likely going to take everything we've got. This graph shows how criteria air pollution varies between different means of commuting, again based on Canadian averages and shown as grams per passenger kilometer. These numbers are valid for vehicle fleets of 2006. The emissions performance of vehicles will improve over future years as cleaner and more fuel-efficient vehicles come into the fleet. The greatest improvement will be seen for NOx and particulate matter 2.5 emissions from large diesel engines such as those used in transit buses. This graph shows similar trends to the comparable greenhouse gas emissions graph you saw earlier. However, diesel performs much better than gasoline in terms of criteria pollutants, as we discussed last week. However, diesel is much worse than gasoline in terms of particulate emissions, although this is expected to improve as older, dirtier diesel vehicles are replaced with newer, cleaner versions. Criteria pollutant emissions vary within biofuel types based on the specific blend that is used. Compared with using petroleum diesel, using biodiesel in a conventional petroleum diesel engine substantially reduces tailpipe emissions of unburned hydrocarbons, HC, carbon monoxide, CO, sulfates, polycyclic aromatic hydrocarbons, nitrated polycyclic aromatic hydrocarbons, and particulate matter, PM. The reductions increase as the amount of biodiesel blended into diesel fuel increases for engines manufactured before 2010. Engines manufactured in 2010 and later have to meet the same emissions standards, whether running on biodiesel, diesel, or even natural gas. Selective catalytic reduction technology, which reduces nitrogen oxide emissions to near zero levels, makes this possible. For these new technology engines, the emissions from diesel fuel are comparable to those from biodiesel and are very, very low. These new technology engines are some of the cleanest engines on the road. B100 provides the best emissions reductions, but lower level blends also provide benefits. B20 has been shown to reduce PM emissions 10%, CO 11%, and unburned hydrocarbons 21% in older engines. Although electric vehicles provide many performance and environmental benefits, two major challenges related to lifestyle and convenience. There is currently a serious lack of charging infrastructure, and it still takes a long time to charge the batteries. So if you need to travel more than 100 miles in one day, which is the maximum current driving range of all electric vehicles, even if you could find a charging station, you need to find something to do while you're waiting for the vehicle to recharge, or find a station that allows you to swap the battery for a fully charged one. These types of issues are the subject of much research and development in the area of electric vehicles right now. And many researchers are working on creating the next generation of electric vehicles to be more convenient and user-friendly than ever. Mark Frohnmayer, in the TED Talk, Dude, Where's My Car?, discusses his experience in creating a sustainable electric vehicle. He provides an interesting overview of the innovation process from initial idea to prototype creation. He also points out that mass transit is making a comeback and suggests that the most sustainable solution to current transportation issues may be sustainable personal rapid transportation, which combines ultra-efficient electric vehicles, car sharing like Zipcar, and smart car technology. This type of technology is being implemented in real life in Masdar City, which is a sustainable city currently under construction in Abu Dhabi and slated for completion by 2020. It will be a carbon-neutral, car-free city where cars are prohibited from entering and circulating. To take their place, developers are creating an innovative personal rapid transit system based on driverless pods that carry passengers from point A to point B without requiring any human-based operation. Hopefully, this week's lessons have given you more information on alternative transportation options that will help you make choices about your own transportation needs going forward. Next week, we will be focusing on what options are available for sustainable heating.